what we have the main, the core feature of Go as it started with, running high concurrency. So our next speaker, Vignesh, is going to talk about Go and concurrency and various different patterns. Please give a loud round of applause also so that we can call the rest of the people in. Stage is yours, Vignesh.
Hi everyone, good evening. I'm Vignesh. I'm a principal software engineer at Tarka Labs, and today I wanted to talk about some of the common mistakes that everyone does while writing concurrent code in Go, and basically talk about the patterns that you can use to fix them, right? In addition to that, I also wanted to point out the impact that these patterns have when you're building a production-grade application like Cockroach DB, right? So let's get started. Perfect. So what is concurrency, right? Concurrency is a way to compose independently executing workloads. Concurrency is not parallelism, right? You're not trying to run multiple things parallelly, right? So a concurrent program can also run on a single processor. And Go's concurrency primitives provide a simple and effective way to express concurrency. So it is, if you're coming from the Java world, I think you would know the pain of writing concurrent code, right? You have to maintain thread pools, threads, and so on and so forth. But here, you get abstractions on top of them where it makes it simple to actually get started with concurrent programming, right? So let's talk about the first concurrency primitive, right? Go routine. Go routine is nothing but a lightweight thread managed by the Go runtime, right? And these threads are multiplexed by the Go scheduler onto OS threads. So usually, whenever you are writing concurrent programming in different languages, you are pretty much creating an OS level thread, which is super heavy, right? But in this case, what happens is the Go routines that are created are managed by the Go runtime. And Go runtime maintains a contiguous stack for all of these threads, all of these Go routines. So the stack can actually grow and shrink based on the number of Go routines that you have, and the scheduler maintains this. The runtime maintains this. So this helps you spin up thousands of Go routines, and they are very cheap to create, finally, right? So moving on to the next primitive, which is channel, right? So now we have all of these threads created, or Go routines created, and there needs to be a medium to communicate between each of them, right? So that's where the channel comes into play. So channel is nothing but a typed conduit for communication between these Go routines, right? And mostly you use them for signaling and data transfer. And these can be unbuffered if you want to do something like a synchronized handoff, or they can be buffered if you want to achieve something like a queue with back pressure, right? Moving on to the next one. So let's start with a quick snippet. So the first issue, if you have been writing Go program for a long time, that you would have faced is unbounded Go routines, right? So if you take a look at the snippet, you have items, and then for each item, you're trying to spin up a Go routine. So when the item count is less, it would not have much of an impact, right? But when the item, let's say the item count increases to hundreds of thousands or more than that, that's when you start feeling the pain, right? What will happen is each one of these items will spin up a Go routine, which basically means they are using up system resources. And eventually, you will end up facing out-of-memory exception or some other error, right? So how do we fix this? So one way to do this is to actually set the concurrency limit, right? So if you see the snippet here, the limit is set to 8, which basically means at any given point in time, the maximum number of Go routines that can be running would be 8, right? And this way, you can control the system resources that are used by your Go routines. So how does any of this matter, right? So let's say you have DB like Cockroach DB running in production, which might be processing thousands of SQL queries per second. And each of these SQL queries will in turn fan out multiple key value operations. And assume that you're creating a Go routine for each of them, this would end up pretty much bringing the system down at some point, right? So in this kind of scenario, a pattern like this would help cap concurrency and prevent any blow-ups in your system, right? Moving on to the next snippet, ignored cancellation and shutdown, right? So if you see the snippet here, we have a stand-in which for a long-running task. So let's say you have a caller, and the caller pretty much calls this code, which ends up creating a bunch of long-running tasks. And assume that the caller exits prematurely, and while the tasks are still running. So in this case, what will happen is the task will continue to run. What I mean by that is the Go routine will still continue to run, and basically you'll have zombie processes running in your system consuming resources, right? So how do we address this? One way to do that is by using context passing, right? What happens here is you use a context, and the caller of this particular snippet, whenever they exit, the context knows about it and calls context.done, which basically triggers onto the child processes, and they can exit gracefully, right? So what I'm trying to say is, pretty much when the parent or the caller cancels, you would have signals being sent to the children, and then they can terminate gracefully, and then the resources can be gotten back, right? So, and in a database like Cockroach DB, you will have clients who are canceling queries while they are still running, right? And it can even be the case that a client basically shuts down for some unknown reason. And during the, when the cancellation happens, we want to make sure that anything that is running downstream, whether it be key value operations or storage reads or anything of that sort, we want them to be canceled also, so that you can recover those resources, right? And the other thing also is, let's say one of the nodes in your database cluster shuts down. We want to make sure that any operation that is currently happening is gracefully terminated, right? So, and again, like I said, this also prevents zombie processes, or in this case, zombie queries, right? So this kind of a pattern helps you avoid getting into a scenario like this, right? Moving on to the next slide. So if you take the snippet that is there here, we have a producer and a consumer, right? The producer basically keeps sending messages to a channel, and then the consumer keeps consuming it. And everything looks pretty much okay here, right? Do you see the problem here? Anyone? Okay, so if you see here, once the producer is done sending all the messages, the consumer does not exit. The consumer continues to listen on the channel, and it's completely blocked, right? So what will eventually happen is, basically this will lead to a deadlock, and your program might panic, and then basically your process, even your process can shut down, right? So how do we avoid scenarios like this? So one way is to have like a single closer, right? Someone who is centrally responsible for maintaining all of these channels and terminating them properly, right? So in this case, it'll be our producer. So if you see the code here, you have a differ statement over there, which closes all the channels, right? So when your producer is done producing all the messages, basically that code kicks in, and then it terminates the channel, right? This way, things don't fall apart. So one thing I wanted to point out is, in Cockroach DB, Raft is used for consensus to maintain the cluster state, right? And the way that this happens is there is a lot of communication happening back and forth between the nodes to make this work. And usually, RAF scheduler has one owner that is responsible for enqueuing these tasks and closing the queue. That way, like, you don't have open channels which are causing, shutdown of the nodes in any way, right, or restarts. So, moving on to the next slide. Allocates forever. So, if you see the snippet here, you have an infinite for loop running here, and then you have a time dot after, which spins up a timer. So basically, this is trying to trigger the do work method periodically, right? So, and like I said earlier, so time dot after spins up a timer object every time it runs. So this is not a problem for short-lived systems, right? But when you have something like a database which is not going to shut down for weeks or months altogether, every time if you end up creating an object, this is going to lead to memory leaks, right? So how do we fix something like that? Going on to the next slide. So one way is to reuse the same timer that you have, right? And by using a ticker, what happens is, whenever you say time.new ticker, it creates one single timer object, right? And based on the duration that you mentioned there, so for example, let's say here it says time.second, which basically means it sends a signal every second, right? And the consumer of the ticker can listen on to that and then perform the task that it has to perform, right? This way, you only have one timer object, and you don't end up, creating multiple objects, leading to memory leaks. So, how does this matter in real life, right? So, in a database like CockroachDB, you have a bunch of these periodically running processes. So, for example, garbage collection, health checks, and other similar tasks are run periodically. And in a database like this, if you have timers getting recreated every time, this can lead to memory leaks, and you totally want to avoid that. So this kind of a pattern helps you prevent these scenarios. Right. Moving on to the next one. So a very similar snippet again, where you're looping through a set of items and then you're performing a work using a Go routine, right? So this looks perfectly fine, but the problem here is, let's say one of the Go routine exits due to an error or there is a sudden panic. In this code, what happens is you pretty much lose all of that information, right? There might be scenarios where you would want to act on any of the errors. You might want to restart the process, or you might want to do additional tasks to fix the error that's happening, right? But in this scenario, basically all of that is lost, and then, yeah, you're not able to act on it, right? So how do you fix this? So one way is to use an error group and then have a panic recovery, right? So if you see the code here, we are basically acting whenever there is a panic, and then you're printing the error over there. And if you see line number 13, we are waiting on the Go routines to finish, and we are also saying that, hey, whenever there is an error, on the first error, log the error out, right? So this way, if any of the Go routines actually fail due to an error, you act on it, right? So how does this matter, right? So in a database, whenever you're running a distributed SQL query, right, parts of the query are being run in multiple nodes. And if any of the nodes faces an irrecoverable failure, you want to make sure that you exit all the routines running on the other nodes, right? So that you don't end up providing inconsistent results. So using a pattern like this, you can achieve that, where during any of the failures that you have, you exit and then take the right action on top, right? and which is what I'm trying to say here, cancels peer on first error and ensures consistency, right? So this is one flow. There can be other use cases also where you might want to collect all the errors that are happening in all the Go routines and then take a action finally, right? So that is also possible here. So instead of actually logging the error on the first error or panic that happens, you can wait, collect everything together, and then while you're exiting, you can take an action. So this is also one of the fixes that you would want to do if you're writing a code like this, right? And yeah, I think that's pretty much all I had. Any questions?